Hello, folks. How's everybody doing? Hope you're doing a little better than me. As you know, I've been in the hospital. They let me out yesterday, and I'll be on antibiotics for another week or so, and then I'll have an operation sometime in December. And that's the rundown. So hopefully, I'm out of it. I'm clean from this big problem. Erysipelas, that's what it's called. Anyways, the other day I had a couple issues that I wanted to cover, and I think I'm going to cover them today. One has to do with this gentleman. His name is Gil B. He put a couple comments, and I want to answer them because they're very pertinent to what we have going on here. The second one has to do with the electric universe and their notion of gravity, especially the speed of gravity. So I want to tackle these two issues today. Okay. And yeah, hello. I do want to thank all the well wishers and all the people who support me. Okay, and really thank you for it. Okay, well let's get on with it. Here's the comment made by Mr. Gilby. Okay, let's put this up here so that you can see what his comment was. His original comment. This was before the last transmission. Okay, he says, "Bill, your theory is irrational. You are not using physical ropes. Physical ropes aren't invisible, nor can a person walk through physical ropes. It's completely irrational to expect anyone to understand the type of rope you're claiming exists. Your ropes are invisible like gravity and the atom, yet they physically restrain all things, but can be walked through as if they don't exist." Okay, so I replied that you can't touch a tri-bar, you can't touch a circle, and for sure you cannot see the air. I mean, those are very common things that everybody can relate to. So Gilby answered. He said, "At no place in my comment do I claim to be able to make contact with 2D things like circles, nor do I claim 2D things are objects, as per your definition of objects, that which has shape." Okay, so the first thing I want to clarify is that this is not really my definition. It's the scientific definition. In science, we do not agree to definitions. In science, we have to fight for and defend our definitions with shield and sword. Okay? And so we can't have 10 definitions for the same word. Only one may remain standing. We have to use it consistently throughout the presentation. Okay? So I have defined what the word physical means. It's a synonym of the word object, of the word thing, of the word body. Okay? That's what physical means. What is that? That's that which has shape. Okay? And I think I've talked quite a bit about that word. I do emphasize the word object because you can't do physics without objects. That's why I think it's absolutely necessary to define this word. Okay, and so the issue is that Mr. Gilby has the ball is in his court. The onus is on him to define the word physical so that we can follow his presentation. And if you look at that first comment that he made there, he says, he talks about physical ropes, and then he talks about them existing. And exist is a very important word in physics. Physics is the science of existence. Physics only studies or analyzes or explains that which exists. So we do define these two words, object and exist. Those are part of the foundations of physics. This is like if you take medicine. You cannot do medicine unless you define the word health or sickness or words of that nature. This is not doing semantics for, trivial semantics for the hell of it. This is doing, setting the foundations for a given discipline. That's what you need to do in physics, okay? So if you look up the word physical, okay, like I did here, I'm going to put it up here. These are the definitions you'll find in the dictionary and in the Wikipedia, okay? Physical, of or relating to the body, Okay, so what is a body? Well, we don't know. We need to define that word. We need to understand what physical and body mean. Of or relating to that which is material. Well, what does material mean? What is that? And they add there the physical universe. Noting or pertaining to the properties of matter and energy. Well, I don't know about energy, but surely about matter. And then the last one is tending to touch, hug, pat. Okay, so they're talking about touch. And I guess that's the notion that Mr. Gilbey had in mind. He was thinking maybe about touch. He raised the issue of touch and see. If you look at the word physical in the Wikipedia, again, it says a physical object or physical body, or simply an object or body, is a collection of matter within a defined contiguous boundary in three-dimensional space. In other words, they're talking about a thing. What is a thing? That's what the word physical relates to, okay? The boundary is usually, and here's the catch, right? The boundary is usually the visible or tangible surface of the object. An object is an identifiable collection of matter which may be constrained by an identifiable boundary and may move as a unit by translation or rotation in three-dimensional space. Okay, what is the problem with this definition? Well, the problem is that in order to touch, you need a second object. You know, you can't do touch all by yourself. You got to touch something else. That means you need two objects to define one object. That's the problem with using the criterion known as touch. The other criterion we don't need is see, because someone else has to do the seeing. Again, you need two objects. And the question I raised the other day is, why didn't people, I've been dealing with this issue at least for 20 years now. And people never ask, well, what does the rope smell like? Huh? What do you mean smell? Yeah, what does it taste like? Nobody asks these questions. What sound does the rope make? Can we go to the lab and test to see what sounds it makes? So nobody asks these questions. Everybody is obsessed with touch and see. And as I told Mr. Gill, we can't see the air, we can't touch a circle. And those are objects, not according to me, it's according to the scientific definition. If he doesn't like the scientific definition, he has a single option. And that is to define the word physical, the word object, the word thing, whichever one of those he wants. In physics, they're all synonyms, perfect synonyms. The word physical means exactly the same thing as the word object. And you cannot introduce words of ordinary speech, indiscriminately into physics. Okay? So, Mr. Gill, if you're out there, the ball is in your court. Okay, but let me continue here. I want you to know something, because if you go to the Stanford Encyclopedia of Philosophy or the Catholic Encyclopedia, well, what you'll find there is they go over this word object or the word thing. What is a thing? They do discuss this, and they're still in the days of Plato. They're still talking about forms. They're talking about things which are not things. Let me give you, for instance, here. This is Mr. Aristotle. Okay, we go back to ancient Greece, and in his seventh book of metaphysics, I pulled out these specific paragraphs just to see where the problem is and why, to this day, people are still confusing the word object of physics with all this philosophical debate that's going on out there. The first one is, and I'm just going to read the dark areas, okay? There are several senses. This is Aristotle. He says this in his book. He says, there are several senses in which a thing may be said to be. So what's the problem there? Well, he confuses object with exist. When we talk about to be, being, he's talking about exist. And we'll find out that some other people made that same error throughout history. Second one, the substance of the thing. They are, some of them, quantities of that, which is in this primary sense, right? Okay, so what's the problem there? Mereology. We have a problem with mereology because people think that an object is what it is made out of. So a table is not a table, not what you're pointing to. A table is all the atoms that make up the table. And that's a problem because, if a table has 1 billion atoms, how is it different than the 1 billion atoms that make up the chair? Okay, so we can't say that an object is what it is made of. That's mereology. And Aristotle made that error. The next one, the words to walk, to be healthy, to sit imply that each of these things is existent. Again, confusing object with exist. Exist is not equal or a synonym of object, okay, of a thing. Exist has something else, and I'll cover that in a minute. Okay, and the last one there, implied in such a predicate. Another major error committed, especially by philosophers today. They confuse the object with the subject of a sentence, that which we can talk about. Okay, an object is not that which we can talk about, because we can talk about motion, and motion becomes the subject of a sentence. That doesn't mean that motion is a physical object. It just means we can talk about it. It's the subject. A noun, yes, but not a noun for the purposes of physics. So that was Mr. Aristotle. Did we do any better? Shortly after, about 100 years later, we have Mr. Euclid. And he wrote his famous Elements, okay? And here you have three of his definitions that relate to object. He says a figure is that which is contained by any boundary or boundaries, okay? That's in book 1, definition 14. Then he continues, a solid is that which has length, breadth, and depth. Terrible, because breadth and depth are not dimensions, okay? Breadth is a vector, and so is depth. Okay, they're motion, whereas length is not. Should be length, width, and height, but that's another lecture. Then book 11, definition 1, a cube is a solid figure contained by 6 equal squares. Again, what it is made out of. So he's got these notions, again, that where he confuses what something is made out of versus what it is. You know, a table is not what it is made of. A table is not 6 sides or 7 sides or the atoms that make it up. No, a table is what you point to. That's what table for the purposes of physics. We get to the 18th century, and we have Mr. David Hume. He was the first one to do this, and followed shortly, well, about 50 years later, by Immanuel Kant. And David Hume says the following in his Treatise of Human Nature, 1739. He says, the idea of existence must either be derived from a distinct impression conjoined with every perception or object of our thought, or must be the very same with the idea of the perception or object. The idea, and this is the good part here, the idea of existence, then, is the very same with the idea of what we conceive to be existent. To reflect on anything simply and to reflect on it as existent are nothing different from each other. David Hume is saying that an object is the same thing as existence. He sees no difference between them. And he says that idea, when conjoined with the idea of an object, makes no addition to it. Whatever we conceive to be existent. About 40 years later, Immanuel Kant, whichever way you say it, by whatever and by however many predicates I may think a thing, even in completely determining it, nothing is really added to it if I add the thing that the thing exists. So these people, both of them, they thought that an object is simply that which exists, and exists is what an object is. They saw these two words as synonyms. Okay, that's where the problem comes in. People think these are all synonyms. That an object is the same thing as it existed, because if it's 3-dimensional, that's what they imagine. Well, if it's 3-dimensional, it's got to exist. Well, does an ideal cube exist? You know, a box exists, but not an ideal cube. That's an imaginary thing. Okay, it's a thing because it's got shape, but does it exist? No, it doesn't. It doesn't have what I'll tell you in a second. For those of you who know what I'm going to say, I'll just keep you in suspense there a little bit. Okay. So where do we go from here? Well, if Mr. Gill wants to answer the question first, I want to make sure that he understands the following. He cannot use any of these. We cannot use any of these as criteria or criterion for the definition of the word physical or the word object. We cannot use the word see, the word touch, mass, volume, motion, move, okay? Made of parts, mereology. Visualized through time, that's also part of mereology. They call them temporal parts in philosophy. Not that which we can use in a sentence. It's not a predicate, it's not a noun, it's not a subject. That's not what a thing is, okay? Has color. Color requires someone to see the color. See, color is a certain frequency, a certain wavelength, but it only is perceived by the observer, okay? The elephant looks at itself and says, I don't have color, or the box, or whatever. Exists, we can't use exists. It's not a synonym of object. It's not 3D because we have 2D objects. Again, all those definition, all those criteria are easily debunked. And is not standalone. It's got to be a standalone object. For example, if you're going to use the angel's halo, halo is not a standalone object. Halo comes with the angel. It's a dependent object. Without the angel, all we have is a ring or a plate. That's it. That's what I'm seeing. If you want that to be a halo, you want it to be holy, if you want it to have some other meaning to it, you must include the angel. You can't do it without the angel. Okay? So all I'm saying is he's going to have to fight for his definition before he can continue. Okay, so why do we need this? Well, the main problem I saw with Euclid especially is that, yeah, he defined a figure, essentially is that which has shape. He called it boundaries. That's close enough, but that wasn't the point. The point, he's never realized how important that definition is for the purposes of physics. And he was doing not exactly physics, but he was doing geometry, which has to do with shapes. Okay? So he should have figured out that you can't do geometry without shapes, without boundaries. Okay? You can't have a triangle, say triangle, and not have some kind of shape in front of you. And it's like, that would have been his first premise. That should have been his cornerstone of his foundations. That's the issue. And so that's why I call it the golden principle of physics. And it goes like this. Physics requires an object. You can't do physics without an object. Object is that which has shape. And there you see some synonyms, including which one? Physical. Number 4 there, okay? The definition of the word object destroys all religions. All religions die with the definition of the word object. Why? Because, well, if God wants to exist, right, he's got to be an object to begin with. And then I'll get to exist in a second here. Okay, so let's go with exist, because that's the other issue that Mr. Gilby raised. Here's his comment. Then you use another straw man, air. Come on, Bill, we both know air exists, okay? But according to your definition of an object, a person should be able to draw an object, okay? Yeah, I agree with that. No quarrel there, okay? If you're gonna define the word object as that which has shape, there should be no reason, no excuse not to be able to draw an object, okay? So, yeah, we agree there. We can draw a table, a chair, a bowl. Show me how you will draw the object air, okay? And then he says, not wind, not breeze, not gust, not a storm. Draw me a picture of air as you like to say. No words needed, just a picture. Okay, I like the challenge. I'll accept the challenge from Mr. Gill. Okay, let's see. First, I want to make sure we understand what the word exist means under the rope model, the foundations of physics. And here it is, existence. The ability of an object, well, this is what you'll find in the ordinary dictionaries, just to make sure that you understand that there is no definition today of the word exist, no scientific definition, okay? And here it says, the ability of an entity to interact with a physical or mental reality. Reality is a synonym of the word exists, so they're using a synonym to define a synonym. That's it. That's what they're doing. It's a circular definition, or like I like to say, no definition at all. In philosophy, it refers to the ontological property of being. So is being the same thing as exist? Well, if you look up the definition of the word being, it says to exist. So that's another synonym. You can't use the word reality. You can't use the word being to define the word exist, because all you're doing is introducing a synonym. Okay. And again, this is not semantics. We need to define the word exist. We need to define the word object, because we can't do physics without it. Those are the foundations of physics. That's why we have to emphasize and harp on that issue. In philosophy, being means the existence of a thing. That's what you'll find in the Wikipedia. So there you have the synonym. Dictionary.com, exist, to have actual being. Okay, great. To be, to have life or animation, to have life or animation, to live. Okay, now you look up the word being, the fact of existing. Existence, something that exists. Great. Be, to exist or live. So all these are synonyms. They haven't defined the word exist. They have no clue what the word exist means. No one has defined it in the last 10,000 years. And we can't do physics without defining the word exist, because physics is the science of existence. Okay, so what is the definition of exist? Here it is. Here we have Mr. God, okay? And you can see that he's got distance from the tree, from the rock, from a man there, and from a table. If God wants to exist, not only does he have to be an object, he has to have presence. He has to have location. That's what David Hume and Immanuel Kant missed. What the word exist adds to the word object is location. You need to have location if you want to exist in this universe. I don't know about another one. Okay, so that's the issue. The issue is that now we have a scientific definition that we can use consistently. Okay, and again, this is not semantics. A lot of people say, "Well, Billy, I came here to do physics, and you're doing all this grammar, all this nonsense." We need to define these terms because we use them in almost every paragraph or every sentence that lecture gives, a dissertation and a lecturer gives at the conference. So everybody uses the word object, everybody uses the word exist, but nobody's ever defined them, and nobody's ever realized the importance of these two words. Not a single textbook of physics begins by defining these terms, and yet we can't do physics without an object. You tell me, if we need a definition or not. Okay, so he asked me to draw the air. Okay, I did draw the air. I thought he must have missed it, but here it is. There's the air. Those little blue dots that are between the man and the wall, those are air bubbles or air molecules, O2 or whatever other stuff we have in the air. Now imagine if we could see the air, then we would not be able to see anything else. All we would see all day is air. Thank God, Mother Nature was smarter and said, no, I'm gonna make air invisible. Otherwise, we're gonna all be blind. Okay. So that's the first one, but see, that's a picture. I'm going to show you something even better. I'll triple that. Here we have NASA, okay, and this is from the space station. That's a photograph of air. That's a photograph of air covering the planet, okay. So so if we get back here to Mr. Gill, we can find out, no, not this one. It's the other one. Give me a second here. Let me find it. Where is it? I think it's this one. Yeah. So here's the issue. The issue is that no, this is the one I wanted. Okay. Anyways, here you can see a picture from the space station. You can see the air around the Earth. This is a photograph. Now, of course, the flat earthers don't believe that man went out into space. There's a lot of other people who don't believe that. Fine. This is for people who believe that we do have a space station rolling around the Earth, that we do have satellites, and that we can take pictures. And you can see that that's a picture of air. And you say, well, Bill, hold it. What do you mean a picture of air? How come I can't take a picture of air down here on Earth? Well, there, because you see the contrast. You can see the contrast against space. So now we have a contrast. Yeah, you can see the air. But let me continue here with another issue so that you can see this. Here we have an astronaut, okay? And think of him, he's going to put air in a balloon. Or it doesn't really have to be air, it can be any gas. Okay? And we're color coded. We're going to take a gas that either has a color already in it. He's going to put it in a balloon. He's going to take it out into space. He's going to pop the balloon. Okay? And now the question is, does that blob that come out of that balloon, does it have shape? Now you say, well, what shape does a blob have? Wrong question. This is not an issue of what is the shape of water, what is the shape of air, what is the shape of, a blob. That's not the question. The question, does water have shape? Does air have shape? Does a blob have shape? And here I can show you that it actually does. Here it is. We have the astronaut, okay? And he's up there with his balloon. He takes it, he pops it, and you can see that smoke, that gas out there. Does that have shape? Yes or no? You tell me. So yeah, gas has shape. Water does have shape. Liquids do have shape. You just throw a bottle of water in the air, right? The water that's in the bottle, or take the bowl of water, just throw the water up in the air and have someone take a snapshot while it's in the air. And then look at the snapshot, see if you see a shape in there. Water does have shape. And it's not an issue of what is the shape of, no, it's a yes or no type of question. Does water have shape? Yeah. If we're going to call water that body, that blob, then that does have shape. So yeah, the definition of the word object is shape, not touch, not see. The universal property all objects have, two-dimensional, three-dimensional, it doesn't matter whether they exist or not. Cube does not exist, a box does exist, it doesn't matter. All objects in the universe have shape. The star on the other side of the universe, which I cannot see, hopefully it has shape, because the word star refers to anything that has shape. And so when you say, here's my rope, my famous rope, do you see a shape? Well, hopefully you do. All ropes in the universe, I don't have to go to Klingon's planet. All ropes in the universe have shape, because the word rope refers to that which has shape. That's why. Okay? You can't say, well, there are some ropes that don't have shape. Then what the hell are you talking about? Okay? So, yeah, the criterion is shape and not touch or see. Okay? Or hear or smell or taste. Okay, and then Mr. Gill also raised a final question, which I need to address also, and this is what he said. He says, I'm not sure how you can see your theory as being rational while using ropes that hold everything together yet impede the progress of nothing or no one. Air resistance is understandable and unavoidable. Air is everywhere, and so are your ropes, but it's as if they don't exist. And again, see, he's got to use the word objects or the word exist. He's got to use the word physical. He's got to get those words. But until he defines them, we don't have any idea what he's talking about. But yeah, why is it so that the ropes hold everything together? Well, very simple. Here's the how we construct the atoms under the rope model. Okay. And you can see that the rope ends in an atom. And what you'll see here is that the rope forks at the electron shell boundary. It coils around, and that's the magnetic thread, the red one there. And in between you have this blue one that goes right across to the other rope on the other side of the atom. That's going to be the electric thread, the one that goes around, magnetic thread. Okay? And there you have your atom. That's why the rope is connected to every atom, because the rope turns into an atom. You can think of an atom as a knot in the fabric of, not space-time, but the fabric of the rope universe, okay? There's a single thread in the entire universe, and this thread goes everywhere, turns into the rope, which turns into a knot we call an atom, which turns into a rope, which turns into a knot, which turns into a rope, into an atom. That's what the universe, that's all we will see if we had the eyes of God, okay? So yeah, that's why it holds things together. It holds things together because all atoms are interconnected by twined pair of threads. It's a DNA-like shape. Okay, you can all understand that. You can all visualize that. And so that's in a nutshell why it holds together. Now, why can we go through it? Why can't we touch it? Why can't we see it? Well, Mother Nature was wise and she made the rope invisible and untouchable. Imagine she would have made it touchable. We would be all tangled in ropes, right? We wouldn't be able to get across, any two atoms. Here on Earth, we got atoms everywhere. So you wouldn't be able to get through anything because you'd be bound by all these ropes. So no, they were wise. God, Zeus, Mother Nature, Father Universe, I don't know, someone out there, they were wise and they say, look, we can't make the ropes touchable. We can't make them seeable because then all these people would be tangled and they wouldn't see anything. So they were wise and they said, no, we're going to make it invisible and untouchable. Okay? So the ball is in Mr. Gill's court. If he wants to answer that, he'll have an opportunity. And essentially, he's got to define the word physical if he's going to be using that. And he's obviously going to have to define the word exists. That way we can follow his dissertation. We know what he's talking about. He says he can't touch an object such as a circle. Well, what is a circle? Is that not an object? And if not, then what is an object? Especially for the purposes of physics. Okay? So the ball is in his court. Okay. Okay. Next issue is the people in the electric universe, and I want to touch upon a specific issue, which is the one that I did not cover last time, and that's what is the speed of gravity? How fast does gravity travel? And if you go to the official version, and this comes from Brian Greene, he did this in his Nova show. I think it was a 3-part series called The Elegant Universe. Okay, and this is what he put up there. Okay, and he says the following, and obviously this comes from Einstein's warp space scenario. Okay, and they say the following: nothing can travel faster than light, meaning that gravity cannot travel faster than light, whatever gravity is. Okay. So what happens? What if the sun were to disappear? Well, according to Newton, everything would just fly off instantaneously, okay? Immediately, And according to Einstein, no, since nothing can travel faster than light, and we are quite a bit far away from our sun, until the information reaches us, I guess along the space-time fabric, it would take us 8 minutes for us to receive the notion that the sun disappeared. So what they're saying is that the information, if you want to call it that, gravity, travels along the space-time fabric at a speed no faster than light. And here it's what they're saying is it travels exactly at the speed of light. So it would take 8 minutes for us to realize that the sun disappeared, and that's when the Earth would start flying out of the solar system. Okay, what does the electric universe have? Well, they propose something a little different, and they say the following. And this comes from a couple fellas. I mentioned one of them last week. Let's see if I can put it up here. Okay. And that's Mr. Ralph Sansbury. He died in 2014. Before then, we had Mr. Tom Van Flandern. And he wrote a paper, The Speed of Gravity, Repeal of the Speed Limit. And that's in his meta research site. It's still available, even though Tom is not. And he says, on the basis of 6 experiments, the lower limit for the speed of gravity is 2 times 10 to the 10th c, velocity of light. Okay, that's what he calculated. Now, I had a talk with Tom before he died, sometime, I think, 2003. And he was a field guy. Yeah, that's what the main subject matter was between us. He was a great fielder. He was a left fielder, infielder. He played center field, right field. He did fields all around. And, I said, look, Tom, there's no such thing as a field. We have the electric and magnetic fields that make up light, supposedly the transverse wave of light. And he could not come to grips with that. He was so involved with the word field that, when someone tells you there's no field, it's like telling a Christian that there's no God. It's like, what are you saying? You're killing my religion. So, it doesn't come in nicely to the ears. Okay. So Tom had a problem with that, but then he had a problem. We talked about the instantaneity of light as well. And you can see here, this comes from Walt Thornhill's site. Okay, and he's quoting Ralph Sainsbury, because Ralph really is the guy who came up with this. And he says the following. He says, Newton's law of gravity does not involve time. Perfect description. You can see the equation at the bottom. Force equals gravitational constant, mass 1, mass 2, over distance squared. Now that distance there, that's separation. That's not distance traveled. So important that people, the mathematicians, they don't understand that. They don't understand, because to them, whether you clock a distance or whether you unroll your measuring tape, there's motion. And so distance for them is always distance traveled. They measure it in terms of meters, feet, yards, whatever. And that's not what this distance is, not in Newton's formula. In Newton's equation, distance is separation between two objects. It's a static separation, quite unlike Newton's second law of motion, force equals mass times acceleration. That acceleration there includes distance traveled. So what's the difference between these two equations? The distance in the gravitational equation is separation, just fixed separation between two surfaces. The distance embodied in the Newton's second law of motion, that distance is distance traveled. And that takes us to the principle of equivalence, Einstein's principle of equivalence, on which he based special relativity specifically. And I'm not going to deal with that today. I'll deal with that next time, more than likely. But let me continue here with what Walt Thornhill said. Newton's law of gravity does not involve time. Correct. There is no time involved there. And that's the equation on the left, the one in red. Okay. This raises problems for any conventional application of electromagnetic theory to the gravitational force between two bodies in space. Correct. Since electromagnetic signals are restricted to the speed of light, gravity must act instantly. Gravity must act instantly. Okay, listen to that. He wrote that, okay? And we're going to see how he backtracks on that. For the planets to orbit the sun in a stable fashion, if the Earth were attracted to where the sun appears in the sky, it would be orbiting a largely empty space, because the sun moves on in an 8.3 minutes it takes for sunlight to reach the Earth. Again, what Brian Greene described or illustrated in The Elegant Universe. Okay? If gravity operated at the speed of light, all planets would experience a torque that would sling them out of the solar system in a few thousand years. Okay, but listen, clearly that doesn't happen. This supports the view that the electric force, listen to this, the electric force operates at a near infinite speed on our cosmic scale, as it must inside the electron. Okay, we got a problem. He's got a little bit of a contradiction. He says gravity must act instantly, and then he says it travels near infinite speed. Well, near infinite speed is not instantly, right? There's a little bit of a contradiction. Is there time involved, or is there no time involved? Newton's equation says there is no time involved. Okay? So all these folks, they're talking about speed faster than light. Tom Van Flander, Ralph Sainsbury, and Walt Thornhill, as well as David Talbot. All these folks are talking about, what is the speed of gravity? They say, well, it's faster than light. That's what they're saying. It's faster than light. It's infinite or near infinite speed. It's instantly, but not instantly. It's, I don't know what they really mean by instantly, if they're going to say near infinite later on and qualify that. Okay, so we got a problem. We still don't have an idea what the speed of light is, except from Mr. Flandern, who says, well, 2 times 10 to the 10th velocity of light. Okay, so here's another issue that they raised concerning the speed of light. Another description, just so we put this into the right context. Okay, and here's what Walt Thornhill says also Quoting Salisbury, that's the fellow that's next to Wall in that picture there. The real nature of light. This, I think, this comes from the paper written by Salisbury, I think in '79 or so. It leaves the question of what the speed of light is. Oh no, this is by Walter Thornhill. Yeah, he says this is where I part company with Salisbury and others who explain it in terms of a delayed response to an instantaneous signal. Look at the words they're used: instantaneous. In my view, the crucial difference between the near infinite speed of the electric force and the relative dawdle of light on any cosmic scale is that the electric force is longitudinal while light is an oscillating transverse signal moving slowly through a medium. Okay, so according to Wall, right, he's the head of the electric universe today, and he says that the electric force is what mediates gravity, and this electric force, for some reason, unjustified, unsubstantiated, says it's longitudinal, whereas whereas the signal of light is transverse. Where he got this, he hasn't justified it, at least in the piece that he wrote that I looked at. And again, you can see on the right-hand side, the speed of gravity, the electric force, he's thinking it's the electric force, is almost infinite on our scale. Well, again, we have the contradiction between instantaneous and infinite, almost infinite, not infinite, but almost near infinite, right? So is it instantaneous or is it infinite? Which is it? I mean, please clarify. Will the real speed of gravity please stand up? Okay, what is the problem? Well, again, I know you come here to do physics, and I give you grammar, I give you semantics. You say, Bill, you're filling with semantics, but see, the problem is these words are irrational. You cannot use them in physics. You cannot use the word instantaneous, infinite, or infinitesimal. In the case of infinitesimal, real quick, what they're saying is something is small and it's also zero volume. So is it zero volume or is it small? See, infinitesimal means approaching zero. It doesn't mean zero. But they use the word infinitesimal because it gives you the idea that something is so small, so small, so small that the observer can't see it. So we might as well consider it or think of it as in existence, of having no volume. That's what they do with a singularity. And you can't really do that in physics because I don't care what SEM or atomic force microscope you use, there better be something there if it's infinitesimal. Approaching zero is not zero, okay? And those who study calculus know that, you take the limit of something, of approaching zero, that doesn't mean zero. It just means approaching zero. That's great for math. Physics is something different. Okay, keep that in mind. You can't exchange one for the other. Okay, so why is this a problem for the electric universe? Well, because every time they talk about speed of gravity, when they talk about near infinite, when they talk about almost instantaneously or even instantaneously, what they're talking about is particles. They're thinking of something that's moving from A to B. Okay, so here is the particle version of Earth going around the sun. And that's what they're saying. They're saying, well, that's instantaneous or near infinite in speed or whatever, or many times the speed of light, any way they want to phrase it. Well, if you do it with particles, you cannot simulate gravity because gravity, if it's instantaneous, you can't send particles from the sun to the earth instantaneously. So there's going to be a speed, and that's the speed that Tom Flander calculated. Okay, 2 times 10 to the 10th c. Okay, so this is the first problem because you cannot simulate really particles with gravity, gravity with particles. Okay. What's the other problem? Okay, this is the word instantaneous, and I'm going to show you a Mona Lisa. You heard of the Mona Lisa? She was painted by Mr. Leonardo. Okay, and here she is. On the left-hand side, you see a photograph or the picture itself, and on the right-hand side, you see her smiling. Okay. Now, is the picture on the right the same thing as the picture on the left? Well, no, because in the picture on the left, on the right, she's smiling. Okay, and she moves her eyelids, she moves her mouth, she moves maybe her nose there or her cheeks. That's a movie. And when you use the word smile, like Mona Lisa smile, right? Famous smile. She doesn't smile in a picture. All she's got is a picture. She's, you can call it a smile, you can call it a frown, you can call it whatever you want, but all those are verbs. Those are okay for ordinary speech. If you're going to talk about Mona Lisa's smile, you're talking about motion within a picture. Okay, that's what you're doing. You're introducing motion inside a photograph or a painting or whatever. And here's a Mona Lisa, but we're going to break it up into little pieces, okay? This is what you really were seeing. You were looking at a movie. And you can see in the first one, you have the original. That's Mr. Leonardo's. And the second one, she begins to smile. Then she raises her mouth a little more and then eventually, returns to her original picture. So it took 5 frames of the universal movie to produce Mona Lisa's smile. Okay? The first one is a photograph. Those 5 frames, that's what you see on the top in green, that's a movie. And she cannot smile instantly. She cannot smile in an instant. The word instant is forbidden in physics because there can be no instantaneous motion. Instantaneous motion is a contradiction, okay? Motion involves at least 2 frames of the universal movie. That's the issue, okay? You need time to do motion. In this case, you can see the t greater than 0. You don't need that for the photograph. Photograph is t equals 0, okay? Okay, so I hope you understand the difference between a photograph and a movie. That's what instantaneous refers to. But you say, well, is gravity instantaneous? Well, Newton's equation says it is. But instantaneous, we have to be very careful of the context. What do we mean by instantaneous if we want to bring it into physics? I'm saying you can't, but if people are so bent on using this word, what does it mean? What is the physical interpretation of instantaneous? How can gravity act, as some of these folks said, instantaneously? And how can you do that with particles? How can you have motion that's instantaneous? And essentially what they're doing is applying Newton's second law, force equals mass times acceleration, because that acceleration has time in it, whereas Newton's gravitational formula does not, okay? Okay, so let's find out. Let's find out what the secret is. Here it is, okay? We have an elephant, and the elephant is falling to earth, okay? In the first picture, the elephant, I didn't draw the millions of gazillions of ropes that attach them to the center of the earth, okay? I show only 8 electromagnetic ropes. You see 1 blue, 1 green, 1 red. They're all on the same axis. Why? Because I don't know if you can see those very well there. You see 3 atoms on the trunk of the elephant there. A blue one, a green one, and a red one. You see blue, green, red everywhere there. All those are atoms. Okay, they're lined up on the same axis. That's why the blue, the green, and the red are on the same axis, on the same line. What happens when the elephant moves 1 millimeter closer to the earth? Of course, here I exaggerated just for the sake of illustration. As the elephant moves 1 centimeter, 1 millimeter, 1 gazillionth of a millimeter closer to the earth, now you can see that the ropes separate, they fan out. Now you can see they're not on the same axis. Now we have, instead of 8 ropes, we have 24 electromagnetic ropes pulling on that same elephant. And we did this only by the location. The elephant hasn't changed its weight, its mass, or anything. All we did was move it closer to the earth. And you can see what happens. The ropes fan out. So you can see I modified Newton's equation. It's not force. It's known as tension. And tension is not a force. It is in mathematics, which it doesn't matter whether you use the word force or tension, because tension is a force according to mathematics. Not in science, not in physics. In physics, tension is not a force. Force, someone wins the tug of war. Tension, no one wins the tug of war. And what you have between any two atoms, between the atom of the elephant, the atom of the earth, is tension, not acceleration or not force. And what happens as the elephant drifts, not forced, but drifts towards the earth, the ropes fan out. What does that mean? That means that your weight, or the weight in this case of the elephant, changes instantaneously if we're going to use the word instantaneous. It means that from frame 1 to frame 2, the number of ropes changed simply because of the location of the elephant vis-a-vis the earth. Okay? That's why Newton's equation works, because the distance in Newton's equation, that distance squared on the denominator, that distance is separation. It just has to do with location. We have two objects, the elephant and the surface of the earth, in this case the center of the earth, fine. And the only thing that changes is the distance between the elephant and the center of the earth. What did that do? That changed the number of effective ropes. That's what I call those, effective ropes. Okay? So I think it's very clear just by seeing this that, people can understand, what the mechanism is. Do you believe in it? I don't care if you do or not. This is not about belief. This is about understanding. You understand the mechanism. That's what I'm proposing. We're done. We're done with science. What continues after that is religion, opinion, belief, proof, that kind of thing, Can we prove this in the lab? No, you can't, because you can't see the ropes in a lab, okay? And just want to also comment on the electric universe's notion of this transverse versus longitudinal. Okay, and here I've got a little picture, a GIF. We have light is a transverse wave. It's slow. That's what Weil Thornhill was saying. And on the bottom you have gravity. Supposedly that's what they're proposing. Gravity is a longitudinal wave. You can see they claim it's faster. And it is faster. I want you to know that during earthquakes, longitudinal primary waves move 1.7 times faster than the transverse wave, the shear waves, as they're known. And that's just to give you an analogy. It's like if you could hear the thunder before you could see the lightning flash. In other words, longitudinal waves do travel faster than transverse waves. But now, we can leave those in the dust, because a torsion wave travels, is much faster than either one of them. And you can prove this to yourself at home if you want proof, you want evidence, you want to do an experiment. Just take your grandmother's, cloth line, tie them to two posts, and tie two clothespins to the ends. Just move one of them. The other one moves instantaneously. That's how fast a torsion wave moves. There's nothing you can imagine, no rocket on Earth that can travel as fast as a torsion wave. Now you know why light is so fast. And since light is mediated by ropes, now you know why gravity is not fast. It's instantaneous, if we're going to use that word instantaneous. What do I mean by instantaneous? I mean that from one frame, universal frame, the universal movie. We have these frames that God can see, or whoever out there. When you go from one frame to the other, as soon as the location changes, the number of ropes changes. That's why Newton's equation is, so-called quotation, instantaneous. Now you have a physical interpretation for why that is so, okay? Okay, folks, and someone might say, well, Bill, did you invent this out of, did you pull this on a bad night, bad dream that you had? Well, no, see, here you have Mr. Richard Muller. He's from Berkeley, and he tells us why the rope is a good model for this. He says, so for example, if you have the Earth, there's this big mass here, and you have you with your little mass here, and he drew the little man there over the Earth, okay? Talks about the big mass and the little mass, okay? Every atom on Earth is pulling on every atom of you. Let me repeat that. Every atom on Earth is pulling on every atom of you. You're also pulling on it. The amazing thing about gravity is that it goes right through things. How else are you going to simulate this unless you have some kind of physical connection between every atom of you and every atom on Earth? Well, here it is. Here's the picture, okay? And you can see why when the earth rotates, man doesn't fly out of the earth, because every atom of his body is tied to every atom on earth. What is the physical connection? What is the mediator? It's the electromagnetic rope. Now, if you want to use cable, you want to use, I don't know, coaxial, you want to use a wire, string, whatever, I don't care. That's fine. All I'm saying is every atom on Earth is connected to every atom on Earth. You can see why it goes through things, because a lot of the atoms are lined up on the same axis. That's why. So we have a simulation, we have a physical interpretation for gravity that the electric universe cannot provide you with, especially if they're going to simulate it with electricity, which is what Walt Thornhill is proposing, saying it's electricity, essentially. They want to do everything with electricity. And for that, if you've seen a couple of my last videos, you need plasma. And plasma means you need atoms, and it means you have to have at least 10 to the minus 3 torr throughout the universe in order to create this the ionization of each atom to produce this plasma, in order to have this current flowing, from one galaxy to another, one star to another. It's just a big mess. And these folks believe that man went to the moon. We did measure in Apollo 14 and 15. We did measure, and 17 as well. We did measure the vacuum on the moon, and it's a 10 to the minus 12 torr. In fact, the solar wind is a 10 to the minus 13, even lower or higher vacuum. So you can't produce electricity. You can't produce ionization, plasma that runs a continuous current with 10 to the minus 11. The facility that NASA has in Ohio, where they test vacuum, they put the astronauts there before they send them out into space. It goes down to 10 to the minus 6. Why is that so? Because after 10 to the minus 5, you can get maybe a little bit of arcing, which is, Zeus sending his thunderbolt, just one here and one there maybe, and that's very rare. I mean, I ran vacuum chambers for 15 years, and I can tell you that arcing does not occur really above minus 5 level. Minus 5 torr, minus 6. When you get to the minus 7, which is where we did operations, we did production, you get no arcing. You get no electricity at that level. If you want electricity, you got to fill the vacuum chamber. It's called the vacuum chamber. You got to fill it up with argon, an inert gas, to the level of 10 to the minus 3, and then you got to ionize it, then you get a current. And what these people are saying, that the universe has 10 to the minus 3 torr if they want a continuous current across the universe. That's how they do gravity. So no, it's absolute nonsense, okay? Okay, folks, I'm going to continue probably with the equivalence principle of equivalence on next time, Sunday. And because it's kind of like a follow-up to this one. I want you to see why Newton's second law of motion is equal. This is what Einstein drove Einstein nuts because he couldn't figure out why they were equal. Why, that's why it's called the principle of equivalence. Why the second law of motion is equal to Newton's gravitational law in the sense that when you're falling to Earth, or when you're standing still on Earth, you're pulled to the center of the Earth. You jump and you fall back, right? We all know this. And your feet are stuck to the ground at all times. So you can stand absolutely still, and you're not gonna fly away, even though the Earth is moving, 30 kilometers per second around the Earth, and it's spinning. And you don't fly out. You're standing still there. Your feet are stuck to the ground. And Einstein said, well, what happens if we take this gravitational G, the gravitation here on Earth? What if we take you to a rocket out there in space where there is no gravity, okay? And we accelerate the rocket at G, a little g, 9.8 meters per second square. We accelerate the rocket at little g, and you get pushed back against your seat, like if you're in an airplane or in a car or whatever, and you get pushed back at the same pressure as if you were drawn to the center of the Earth. And that's Newton's second equation. And you say, well, how can Newton's second equation here in a rocket in space be equal to the gravitational tug that we have standing still on the surface of the Earth? That's known as the principle of equivalence, and I'm going to deal with that on Sunday. Well, I'll see you then, folks, and wish me good luck with my health. I'll see you then. Bye-bye.